In this lecture, we're going to discuss about matrix norms. So we've already seen vector norms. This is an extension of the idea of norms to matrices. Okay. First of all, what we're discussing in terms of matrix norms is applicable to square matrices. So the definition which we're using will be for square matrices. So we already know that matrices are a rectangular array of numbers. So we'll be dealing with n cross n matrices here. One way of finding a matrix norm is you convert this rectangular array to an n squared vector, n squared cross 1 vector, and take the vector norm of this. This is a matrix, you convert it to a vector, and take the vector norm of it. This is one way of doing it, but there are other ways you can define a matrix norm. So let's look at the definition first. The function So for matrix norms, we'll be denoting them using 3 bars. This is a function from R n cross n to R is a matrix norm if for all A comma B belonging to the space R n cross n, if it satisfies these conditions. First is the non-negativity property, which is very similar. In fact, the first 3 properties are similar to what we have in vector norms. So this has to be greater than or equal to 0, where equality holding, this is actually the non-negativity. Equality holding, and A is equal to 0. If and only if A is equal to 0. This is known as the positivity property. The next property is the homogeneity property. So we have C times A, that is equal to modulus of C times the norm of matrix A, where all C belong to the field. This is the homogeneity property. The third thing is what we have, that's the triangle inequality. Matrix norm of A plus B is less than or equal to matrix norm of A less matrix norm of B. This is a triangle inequality. And these are all the properties which we have for matrix vector norms as well. But for matrix norms, it should actually satisfy an additional property which is known as submultiplicativity. So this is actually inequality which describes about the product of 2 matrices. So the product of AB, the norm of that, matrix norm of that should be less than or equal to the matrix norm of A times the matrix norm of B. So known as the submultiplicativity property. If all these 4 properties are satisfied, it is a valid matrix norm. So if only 1 to 3 is satisfied, it is called a generalized matrix norm. And similar to that, if 1A is omitted, not satisfied, it is called a semi-norm. This idea is similar to what we had as a prenorm and semi-norm, but there's nothing called prenorm here. Prenorm, of course, does not satisfy triangle inequality. Okay. So now let's look at a few consequences of these properties. First thing is, we already know that from submultiplicativity, we have norm of A squared, which in fact is norm of A into norm of A. It is less than or equal to norm of A times norm of A, that is norm of A whole squared. So the norm of a matrix squared is always less than or equal to its individual norm whole squared. Okay. Then there's a specific case of this if A squared is equal to A. What are such matrices called? A squared is equal to A. What are idempotent, right? This matrices is called idempotent matrices. Yes. For idempotent matrices, squared is equal to A. In that case, norm of A squared, we already know it's less than or equal to norm of A whole squared. But we know A squared is already equal to norm of A. So norm of A is less than or equal to norm of A squared implies 1 is less than or equal to norm of A. So what does this mean? We already know that norm is uh, always greater than or equal to 0. But for an idempotent matrix, norm is greater than or equal to 1. Okay. Is there any famous idempotent matrix? So I squared. I is a famous idempotent matrix. I squared is actually equal to I. So for an identity matrix, norm of an identity matrix, matrix norm of an identity matrix is always greater than or equal to 1. It's actually a tighter bound. We know it's between 0 and infinity. But for an identity matrix or idempotent matrices, then its value is always greater than or equal to 1. There's another interesting property. If A is invertible, means an A inverse exists, right? Then we know I is equal to A inverse into A, the same as A into A inverse, right? The norm of I is equal to norm of A into A inverse. You can use submultiplicativity, which is less than or equal to norm of A into norm of A inverse. From that, norm of A inverse is greater than or equal to norm of I and norm of A. So if you, for any matrix norm, this is actually an inequality, not an equality. So if you have, in fact, this is why you have, this is also equal to greater than equal to 1 divided by norm of A inverse. Right, this is a tighter bound, okay, because norm of identity matrix is always greater than equal to 1. This is also another interesting result. Let's look at another important remark. We can actually find matrix norms using the ideas from vector norms. So, if you're extending ideas from vector norms, for example, L1 norm of a matrix A, it is defined as the sum of for all IJs till n magnitude of Aij. So this is actually, suppose we have a matrix like this, which has entries A1, A1, 2, etc., A1n, etc., etc., ANN. So but what basically we're doing is we are taking the modulus of all the terms of the matrix and adding them together, which is similar to what we have for vectors for L1 norm. But note that here we denote that matrix norm by two bars, because once we borrowed it, this idea exactly from a vector norm. And also note that if you make this into an n squared vector and uh, apply this norm on this, the result will be similar. So it's actually one and the same. This is this is a valid vector norm. Vector norm. But valid vector norm in the sense it satisfies all the four properties of a vector norm. All the three properties already we know from so we have to just do the submultiplicativity property. While this norm, like L infinity norm on matrices, which is basically the max of this term, is not not a matrix norm. In fact, it turns out that n times infinity is a valid norm. This we can actually try to prove maybe in the next lecture. Okay, let's end this session here.